In this video, we're going to talk about haloalkanes and their properties, their reactions and mechanisms and such forth. So first of all, haloalkanes are carbon bonded to any one of the halogens. So we generally will only use these halogens here, but you can have acetine as well. And how this forms compounds with the halogens forms some interesting chemistry. So starting off with the rules for naming haloalkanes. Right. First rule, functional groups are named in alphabetical order. So if that is the case, we put a name up for you and then we say, right, okay, let's draw this. So I want you to try and draw this before I do. So 1 bromo, 2 chloro. So first of all, the functional groups, you can see functional groups in this case are the bromo and the chloro, and they're named in alphabetical order. So B comes before C. All right, and if we're going to draw that, and I'm going to draw that in skeletal formula for you, it's propane. So that basically means it's 1, 2, 3, 1, 2, 3. And we've got a bromo on position number 1. And on position number 2, we've got a chloro. Okay, so you've got your nice drawing there and you're following your rules. Now the next one, our next kind of rule is use the lowest numbers possible. So if we reverse it this time, and we're going to give you a structural formula this time, I'd like you to try and name it. So stop the video and try and name it. And you've got to use the lowest numbers possible. Now we've already used the lowest numbers possible in the above example because 1 bromo, it's the lowest number we can go to is 1. So we started there, but we've made it alphabetical as well. So remember, you're going to have to make this alphabetical as well. Anyway. Right, let's go for this name. So first of all, we need to find out how long it is. 1, 2, 3, 4, 5. So we have got 5. So that basically means we are going to have to write as our parent chain is going to be pentane. Okay, so pentane, let's make that pen go a bit stronger. Pentane is the length of the chain. And then from the length of the chain, we can start saying, well, what is on the chain? Is it a straight chain? Yes, it is. So we don't have to do methyl branches or anything like that. And we can see that we've got a bromine on position number 1, 2, 3. Or we've got a position, because we can go from either end, position 1, 2, 3. So this would be 3 bromo, whether you started from this end or from this end. And then you've got the chloro. The chloro can be 1, 2, 3, 4, or it could be 1, 2. Well, we want to go for the lowest number possible. Okay, it's really important we go for that lowest number possible. Because we're going for that lowest number, chloro at position number 2 is going to be the lowest. So writing these neatly is quite hard. Remember, alphabetical first, so you're going to have to go bromo, and then you're going to have to go chloro. And if we have multiple bromos and multiple chloros, we put dibromo, tribromo, and things like that before. And we have to put a number for every single group that is on there. So if you have 3 chloros, it would be 1, 1, 1, for example. But anyway, if we look here, we know that the chloro is 2, so we put 2 like that, and we know the bromo is 3. So we've got 3 bromo, 2 chloro, so we've got the alphabetical order, and we've got the lowest possible numbering system. So we're now going to go on to compare the boiling points of haloalkanes. So boiling points increase as you increase the size of the halogen atom. So the size of the halogen atom goes up as you go down the group. So you go down the group, you can see it's getting larger. But it's getting larger because we have more electrons. So more electrons means that we have stronger London forces. Now, we also have more electrons if we have a higher number of halogen atoms. So it's still all about those electrons. Okay, it's just about you get this stronger London forces, stronger induced dipole-dipole forces. Okay, but we can just say in our marked schemes and in our questions, the reason is increased number of electrons, stronger London forces. And you can see this if I show you here, so a couple of boiling points. You can see here I'm going from fluorine to chlorine, both methane, so fluoromethane, chloromethane. And you can see that fluorine is smaller than chlorine. Chlorine has more electrons. Because chlorine has more electrons, the CH3Cl should have a higher boiling point, and it does. Okay, if we go for the next one, and we can say we've got Cl2 versus Cl3, well, there's more okay, halogen atoms, so we've got more electrons, okay, so therefore CH3Cl should have a higher boiling point, and it does, okay, so both of the rules absolutely work, and just make sure you put that on your marks, on your questions, and you'll see it in your mark schemes. So now we've talked about the boiling points, and we're really talking about the fact that there are multiple kind of halogens within one compound, for example, or comparing directly to halogens. And that's usually down to electrons. But actually what haloalkanes can do is they can form permanent dipoles. And because they can form permanent dipoles, they can actually be slightly miscible in water. So that means they can mix with water and they don't form layers all the time. Now if they're short, I'm going to show you two examples of short ones. So if I just go for my, there you go, and this is your chloromethane. So you've got chloromethane and you're going to put a dipole on that. So that is a dipole because the electronegativity of the chlorine is more electronegative than the carbon, and it's pulling the electrons towards itself, so it's delta minus. But if you're not sure about that, please watch the video on electronegativity. So if that is the case, what you can do is you can put that next to water, and that's minus. Now when you think about water, what's the part of water that's plus that would be attracted to that? Well, that's the hydrogen. So we have got that, and we're now going to put our dipoles on. Again, oxygen is more electronegative than the hydrogen, so it's going to be delta negative, and that's going to be delta positive. Right, and then all we do is we think, where does the attraction happen? Well, it happens between the plus and the minus, and it's a kind of permanent dipole-dipole attraction. And because it's a permanent dipole-dipole attraction, okay, you get an attraction between the water and the haloalkane. Because of that, you'll get a slight bit of miscibility. So they tend to be a little bit miscible with water because of these attractions. Now, that happens in two ways. So you could draw it like that as a permanent dipole-dipole attraction, or if I draw it again, you can see here, and people don't draw these normally like this, so it's really good to practice. If I put delta positive there, and I put delta negative there, and then I put the oxygen here. Now remember, the oxygen is negative, okay, in terms of delta negative. Okay, and so you're going to get attraction between that negative and that positive. So you've got a positive there, negative there, so you're going to get attraction. So that can cause them to be slightly miscible. Now, when does this not happen? Okay, this doesn't happen if the carbon chain is too long. So it only happens if you've got short chain hydrocarbons, because the actual chain, the hydrocarbon, is hydrophobic. It doesn't interact with water, and it disrupts any form of permanent dipole-dipole. So this miscibility only happens if you have haloalkanes with relatively short chains. So now let's talk about bond enthalpies. Now, bond enthalpy is the amount of energy required to break 1 mole, and all of the definitions are based around 1 mole, okay? But this time it's in the gaseous state, and you can get asked that in the exam, so it's well worth writing that down if you're making notes right now. Now, we're just going to talk about 4 different types of bonds. So carbon fluorine, carbon chlorine, carbon bromine, carbon iodine, and look at those bond enthalpies, how much energy it takes to break those bonds. Now, I think it's really useful to look at this like this. So imagine the carbon that size. This isn't to scale. Okay, it's deliberately to show you the huge difference. So fluorine, chlorine, bromine, and iodine. See, it gets larger. Now, when you think about distances here, so I'm going to remind you of the definition of covalent bonding. So the definition of covalent bonding is the electrostatic attraction between a shared pair of electrons and positive nuclei. So the positive nuclei are right here, right in the centre of these atoms. And they are attracted to the pair of electrons that's in the middle here. So they're really close to that pair of electrons. Okay? Whereas if we go here, there's your pair of electrons being held in place. And they're held together by that nucleus here and that nucleus here. Now, notice the distance is going up. So the pair of electrons in the bond is here. Okay, there's the nuclei holding it in place, and there's the nuclei. So it's getting further apart. Now, if the nucleus is further apart, and it's obviously got other shells of electrons in between it as well, the hold on those electrons is going to be weaker. okay, because it's just further away. Imagine that an analogy, you're holding on to something like this. You can hold on to it much stronger if it's right close to you like that than it is if you're reaching for it like this. Okay, so therefore it's going to be weaker as you go down because this increased distance. So exam point though. Exam point, the atomic radius is increasing. You're seeing it's increasing right here as you go down the group. Decreased attraction between the nuclei and the shared pair of electrons. That doesn't always get you a mark, but it fully explains it. Okay, means you have weaker bonds and a lower bond enthalpy. Okay, and therefore takes less energy to break the bond. So these are your exam answers when it comes to why does the bond enthalpy, okay, decrease as you go from fluorine, for example, all the way to iodine. And this is why, interesting point, on your non-stick pans, there's something called Teflon, and Teflon's absolutely full of carbon fluorine bonds because they're very, very strong and they don't break, which means your food doesn't stick to your frying pan, which means your food tastes nice. So we're now going to move on to a reaction, so hydrolysis. Hydrolysis is where you add OH- or H2O, and there'll be many more examples of hydrolysis as you go through the course. We're just going to do the one in this example of OH- hydroxide, usually added through sodium hydroxide. Now, really important thing to notice in the future, there's two types of title. There is the reaction, the type of reaction, which in this case is hydrolysis, and the type of mechanism, which usually consists of two words. It's either electrophilic or nucleophilic, or it's addition or substitution, or in some courses elimination, but we don't do elimination in this one. So basically you've got to learn each one of these. Now if that's the case, this is your kind of reaction. We've got bromoethane here, so it could be chloro, it could be bromo, it could be any halogen. Doesn't really matter, it can be any length. And you add it to hydroxide. The hydroxide is then going to make an alcohol, and it's going to substitute out the bromine. So the OH will substitute out the bromine, kick it out, and that's where you get the word substitution. And we'll show you that in a mechanism in a minute. But you can see here that it's nucleophilic. So nucleophilic means that that's the nucleophile. So if that's the nucleophile, and we're substituting, okay, that's why it's called nucleophilic substitution. Now, what are nucleophiles? I just want to do a little bit of a recap. So they have the ability to donate a pair of electrons to form a covalent bond, and sometimes they have a negative charge. So we'll keep that up to the side, okay, and go through some examples. So hydroxide, the one we're going to use today, the lone pair of electrons, okay, which will be donated to form the bond, is on the oxygen here. You can see that pair there. We can also have cyanide, you'll use that in your second year, and the lone pair of electrons is on the C. Again, both of these have negative charges. Ethanoate, the lone pair of electrons is on this O-, and we'll draw that out properly when we start doing further reactions next year. And then water, you're getting onto our neutral species here, where the lone pair of electrons is on the oxygen, and then ammonia, where the lone pair of electrons is on the nitrogen. But don't worry about any of these for now. We're focusing on this one, and we actually will focus on that one as well. Okay, now let's look at how you do the actual reaction itself. So there's a bit of a tip, and I'd write this down if I was you. If you don't know how to do a reaction, it says, can you write down a practical procedure for doing a reaction? Just do reflux. Because everything is done through reflux apart from oxidation of aldehydes, oxidation to form aldehydes, which is distillation. So you've got all of the apparatus right here. Why don't you try and stop the video and try and draw reflux. Okay, so don't just watch the video, try and draw reflux. So let's put this together for reflux. Okay, so we've got our reflux condenser, really important that you label it, okay? And it's also really, really important, I've got the in and the out here, but it's really, really important, I've seen this on mark schemes very recently, that you put water, okay, water in, and then you can leave the out, it's fine. Water in, out, it makes complete sense now. But having the water there means sometimes on mark schemes you don't get the mark. So let's just be thorough and put it on both, okay? So water in and water out. And that water goes in at the bottom and out at the top because it forces all the bubbles out. It forces all the air out, so it keeps everything nice and cold. Because what you want is you want your reaction mixture, which we've got here, which is your haloalkane and your sodium hydroxide. Remember, this hydroxide comes from a metal hydroxide like sodium hydroxide or potassium hydroxide, both work, okay? And you put them in there and then you do heat it and then you boil it and then it evaporates, gets to this nice cold jacket here and then condenses and comes back down. And therefore you never lose any of your reaction mixture, okay? Which means also, and this is a really important exam point, never put a bung in the top of this. It seals it up, pressure builds up and it would blow up in the lab. But if you put a bung in it and you're drawing it, okay, you will lose your marks because you cannot have a bung in the top. You need to have it open, okay, because the liquid doesn't escape because of the condenser, but obviously the heat is still hot going up here, which means the air inside expands, which means it would blow off the top if you put a bung in it, so it wouldn't work. So please don't put a bung in it when you draw it. You will lose your marks. Right, okay, so let's do the mechanism. So we've gone over reaction mechanisms in a previous video called reaction mechanisms. If you haven't done that video yet, have a look at that video and you'll go through heterolytic and homolytic fission. Now this is an example of heterolytic fission. So we've got this thing down here, right, and all we're going to do is we're going to draw it out, and I'm going to draw it out in displayed to start off with right here. Now, when we're doing mechanisms, there's a way in which I do mechanisms which works out for A-levels perfectly, okay, is first of all draw your, whatever you're drawing out. We've got bromo ethane. Second step is draw your dipoles. Okay, so you've got your dipole there because bromine is more electronegative than the carbon. You then draw your other part and you can see here is my OH minus. Okay, and from the previous one, hopefully you remember that you've got a lone pair of electrons right there. So we've got a lone pair of electrons right there. What we do is after we've drawn everything and we've done our dipoles and we know where all our charges are, we know where our electrons are, okay, we know that electrons are negative and electrons are going to flow towards a positive. So we're going to take those electrons to the positive. Really important thing, that arrow can be wiggly all over the place, and that doesn't really matter as long as the end point is the atom that you're going to bond it with. Don't point it towards the charge, point it towards the atom that it's going to bond with. And that's showing you're moving that those pair of electrons between the oxygen and that carbon and forming a bond between the oxygen and that carbon. Next step is count number of bonds that you've got, because this is now a bond. So 1, 2, 3, 4, 5. That's 5. Carbon can only have 4 bonds. So I need to get rid of a bond because carbon can only have 4. So the way to get rid of a bond is usually to place the electrons that are in a bond onto an electronegative atom. Because an electronegative atom can attract a bonding pair of electrons. It likes a bonding pair of electrons to be with it, so it attracts them towards it. So basically, these pair of electrons just go wee like that. Okay, and they go on to there. Now, if that is the case, that's where your substitution is happening because your OH is coming in for your Br. So again, don't let me don't just watch this. Try and draw the products yourself. Okay, and then all we do is we go back here and we draw our carbons. But now we know we've got an OH. Notice I'm drawing it in full displayed formula now. I've got my bond between the O and my H. Okay, and then we also have our Br. Now here's the important thing. Finish it off, draw your charges, know what your charges are. Well, I'm taking 2 electrons here. There's 2 electrons in this bond. They're going out onto the bromine. One of those electrons is from the carbon. One of them is from the bromine, because it's a covalent bond. Which means the bromine essentially is gaining an electron. It's gaining the carbon's electron from in that bond. Which means the bromine's got an extra electron, so it's a minus. Okay. All of these have the right number of bonds. Oxygen has 2 bonds, hydrogen has 1, carbon has 4, so there's no charges on there whatsoever. Okay, so this is the most basic mechanism you will do, and the easiest one you'll do. So it's really important that you understand it so that you can go further on and do the more complicated ones. It's just, I'll go through the steps again. So you will put your charges on, your dipoles. Always put your dipoles on. Start with dipoles, because that's always a mark in the exam. Okay, take the lone pair of electrons or the charge to the positive or delta positive, okay? And in this case, it's a delta positive. Something of note, you can take that arrow from the minus as well. It doesn't really matter which one you do. It is perfectly correct to take it from the minus or take it from the lone pair. And when that goes in, that kicks out because you've got too many bonds to the carbon, and you get your alcohol and you get your bromide. Now, if in the exam they say sodium hydroxide, this would change this equation just ever so slightly. So I'm going to just draw this for you, just with sodium hydroxide. Okay, and we'll draw it down here just as a normal formula. So for example, let's just do CH3, CH2Br plus sodium hydroxide. Okay, so we've added that. Normally it's just OH minus and you can do that. But if they say sodium hydroxide, you've got to include the sodium. If that's the case, you make your alcohol again. We do hydrolysis, nucleophilic substitution to make our alcohol. Okay, but this time we've got sodium in there. It's kicked out the bromine. The sodium is a plus charge, so all we'll get is sodium bromide, NaBr. So basically, if you're in the exam and they tell you to include sodium, they're never going to tell you to include sodium in the mechanism, by the way. It's just if you write the equation. If they tell you to include sodium, it just means your product is NaBr instead of Br minus. Remember, this is hydrolysis type of reaction and nucleophilic substitution. So you have seen hydrolysis using sodium hydroxide, but now we're going to do hydrolysis using water. And the water reaction, when you do hydrolysis, you can actually determine the rate of hydrolysis and the strength of the carbon-halogen bonds. And hopefully you remember from the start of the video the relative strengths of the carbon-halogen bonds. But we can prove this using this reaction. So what we do is we take the haloalkane and we heat it with aqueous silver nitrate. Now the aqueous supplies the water, and that's your nucleophile. We put ethanol in just to make sure everything mixes together properly, because even though you can get some miscibility with haloalkanes, the ethanol makes sure it properly all goes together. Now, our hal is an alkane group or alkyl group connected to a halogen. So hal stands for halogen. You see the water substitutes in, makes an alcohol. You get the halide ion right here, and you get a H+. That halide ion can react with silver because you put silver nitrate in, and you get the Ag+ plus the halide goes to the silver halide, and that should remind you of a reaction that you did earlier in your analytical tests that were in module 3. And when you add silver to certain halides, you get certain coloured precipitates, and we'll go through those coloured precipitates soon. Now what you can do is you can calculate 1 over time depending on the time taken for the precipitate to appear. I've also highlighted something else here which is often missed when people write this down. Don't forget to say you heat this whole thing up. So you've got to heat this whole thing up to happen. And what we normally do is just take a beaker and we take a kettle, we warm up some water and we put it in the kettle, and then we put some test tubes in, just like this. Okay, so we've got 3 test tubes. Those test tubes have 3 different haloalkanes in them, okay, and they're heated with just boiled water, okay, and put in with silver nitrate and ethanol to make sure everything dissolves. We're going to calculate how much time it takes for the precipitate to appear. So in this one, we can see a precipitate has appeared already. It's the yellow one, and the yellow one is silver iodide. Okay, hopefully you remember from previous learning. That's after 30 seconds, and then after 90 seconds, you get this cream precipitate here, which is silver bromide. And then after 150 seconds, you get the white precipitate, which is silver chloride. So that means that there was a chloro in this one, there was a bromo in this one, and there was an iodo in this one. Or let's do it better with the colours. Here is your chloro, here is your bromo, and here is your iodo. Now it took different lengths of time for them to happen. So it didn't take very long for the iodide, for the silver iodide to form. That must mean the bond between the iodide and the alkane must have broken quite easily. That freed up the iodide here, which then reacted with the silver, and then you got this lovely precipitate. And then it took a little bit longer for the bromo to break its bond with the alkane and then form the precipitate, which means the bromo bond must be a little bit stronger than the carbon-iodine bond, and then the chlorine took even longer, which means the chlorine must be stronger. Chlorine-carbon bond is stronger than the carbon-bromo and the carbon-iodo. Now, what we'll do, put that down right here, okay, and then what we'll do is write out some equations. So if we're writing out some equations, let's have a good think, shall we? So, first of all, we know that the Ag plus is aqueous. Okay, I'm going to do 3 of these, so Ag plus aqueous, and then underneath Ag plus aqueous. So we've got 3 equations starting off with that. And then what we're going to do is we're going to add to those our different halogens. So we thought it was starting off, we're going to start with chlorine minus aqueous, and then we're going to go to bromo minus aqueous, and then iodo. Okay, right, so we've got those 3 coming there. Now, if that's the case, let's put the arrows on. I'd like you to complete all of these, so see if you can do them yourself. So what are you going to create? What are you going to create? So if we create this here, we say silver plus the chlorine is going to be silver chloride. Silver plus the bromo is going to be silver bromide. And then we've got silver iodide. Really important thing on all of these are all solid. And if you're ever doing any of these, you have got to put the state symbols in. Okay, so we've got all of that. Now, if that is the case, what we can do is we can look at each one of these and say which precipitate do we think they're going to be. So the silver chloride is going to be the white, and I'm going to shorten it here to PPT. But please, in the exam, don't shorten it to PPT. Put white precipitate. It's just so I haven't got a lot of space. And then we've got our cream precipitate, and then we've got our yellow precipitate. Okay, so we've got all of those that we've seen, and we can see them in our test tubes down here. Now, the one that took the longest was the chloro. Okay, that means, and so what we're going to write here is basically took, and we'll write down the longest time. Okay, therefore it is the strongest bond. Okay, so it's the strongest bond, and that means basically it has the highest bond enthalpy. Okay, and we know it's got the highest bond enthalpy because it took the longest time, the strongest bond, and we'll just write that down, the highest bond enthalpy. Okay, and we can say the opposite of this. So this one took the shortest time, therefore the weakest bond, therefore the lowest bond enthalpy. Okay, and it basically means it takes more energy to break this bond, and it takes less energy to break the carbon-iodine bond, so you can create this. So you've got 3 equations that happen because the carbon-halogen bond broke and was broken by the water. Okay, so make sure you can do all of your ionic equations for the creation of these precipitates. So in the reaction, you add a haloalkane to aqueous silver nitrate, you get your water, and here's your water out of that. Okay, that water then acts as a nucleophile with your haloalkane. So we want to show you the mechanism here, but we've given you the starting materials, the intermediate, and the final product. And this question might be worth 3 marks or 4 marks or something in the exam. Okay, you don't need to know this mechanism. What you need to do is be able to recognise how to put the arrows on when you've got the intermediates, and that's perfectly allowed, a perfectly acceptable question. But you don't need to remember this per se. Right, okay, so let's go through how we would do it, or please stop the video and try and do it yourself. Right, okay, so first of all, I've gone through it before in the previous example. Let's put on our dipoles, and let's put on and know where our electrons are. So there's our dipole there, Okay, so we've got delta plus and a delta minus. We also know that there's dipoles on here, but at the same time, we know that there's a lone pair of electrons here. Okay, in fact, we know there's two lone pairs of electrons here and here. So we've put all our electrons. We can also put dipoles on there, but we know that's attacking. Okay. Now, if that is the case, there's no charge on this, so we can't take an arrow from a charge. We have to take it from a lone pair of electrons, and we have to take it to the atom that's got the plus on, because the negative is being attracted to the positive. Okay, and we take it up there. We know there are too many bonds to this, so we have to kick one out, and it's exactly the same as we do before. But there's an important thing here. Even if you don't know that, thing, look at this. So if you're unsure in the exam, it's got the water attached to the carbon. So that means you must attach the water to the carbon. The bromine is no longer on, so you must kick the bromine out. Okay, so really, really important that you kick it out just like I'm doing here. So we've done our first step, and if we're talking about marks, okay, that will get me 1, and that will get me 1. And the dipoles sometimes will even get you 1. So 3 marks just in 1. It's a lot of marks for a question like this. And then you go on here, and sometimes they give you the charge, okay, but I'm not going to, because I'm going to explain it to you. There's a general rule. General rule is if you have nitrogen or oxygen and you add extra bonds to a nitrogen or oxygen, it will be positive. So for example, if nitrogen has 4 bonds, the overall is going to be positive. If oxygen has 3 bonds, because oxygen is only meant to have 2, then it will have a positive overall. Now, often they'll just put that positive on there for you and not make you work it out. Now, if you want to work this out, you can count all the electrons in these bonds and you'll find you have 1 less electron than you do have protons. But I'm not going to waste time doing that in the video. Now, if that is the case, you've got a positive here. Now, I want to get rid of that positive. I know that the H leaves. And I know that it leaves as H plus, which means it loses an electron. So there are 2 electrons in this bond. One of them is of the hydrogen. So basically, I need to take the 2 electrons in that bond, or at least the hydrogen's electron, and I need to take it away from the hydrogen because I'm making H plus. So that means I need to move these 2 electrons. Now I've got 2 options. I can move it down here to the H, which is commonly done by students, or I can move it up to the oxygen. Now I'm telling you why you don't move it down to the H. If you move it down to the H, you're adding 2 electrons to the H. That hasn't got any electrons, so you can't move the electrons down to the H, which means the only way it can go is to the oxygen. Now, why does that make sense for it to go to the oxygen? It makes sense it goes to the oxygen because the electrons in the bond are negative, and if they go towards a positive, it makes sense. Negatives are attracted to positive, and it cancels out that positive. It returns one of the electrons to the oxygen, because remember, one of these electrons in here is the oxygens, and it gives it an extra electron from the hydrogen. The extra electron cancels out the positive, and therefore you've got a nice neutral species down here. So that means basically you're going to get another mark for that. So you could get up to 4 marks for a question like this. And I think once you've done it a few times, it's not too difficult, but you've got to practice it quite a few times to do it. And there are multiple examples of where they can do this. And I would genuinely say try and do as many as possible through the worksheets and the practice exams that we produce.